Thank you everyone. This is a lecture about interpretation of data and handling data. And what I'm going to seek to do in this lecture is to describe what I think data science is as it is presented and used and professionally practiced now, and also to describe an alternative approach to data, which we at BT call the science of data. And I'd like to just say that this is not my work only, although I have contributed to it, but a lot of people at BT Research have been key contributors here, and I'd particularly like to thank Rob Claxton and his research group, who've been a driving force in developing data science and big data at BT over the last 5 years. So, as I say, this is about interpretation. Years ago at BT, we built a very innocent and helpful application, which is the type of application which is in common use today. People call it social CRM now, but in those days we were simply trying to help BT customers by going onto social media, intercepting posts about BT that were publicly made, and then turning that round to agents who could help the people with their problem and responding to customers' problems. And our interpretation was that this was to help customers solve problems with their broadband. But the Daily Mail's interpretation was that we were spying on our customers and spying on Facebook in general. So this is a great example of how technology can be misinterpreted and how data can be used in one way or another way, depending on what you want to do and how you want to present it. I said that this lecture is not just my work. I work at BT. I work at BT Labs, which is on the Suffolk coast, just about 5 miles outside Ipswich. And BT Labs is called at Astral Park, and we are about 170 research scientists working on a campus of about 3,500 BT people, and with about 1,000 non-BT people now. So this is a proper technology campus with a cluster of startups, a cluster of third-party companies, and this is one of the nexuses of research and development in the UK. It's probably the only ICT, privately run ICT research lab in the UK now. So this is the place where my work is generated. As I say, we have a whole load of non-BT people working there, but not only that, we also bring a whole load of students and VIPs and pupils from schools, and we convene them onto the site and use it as a way of communicating the developments of technology which are vital to getting our services, our broadband services and our communication services used. I'll move this on. Go past the ICTs cluster I've talked about. At Astral Park is just one of the places that BT does research around the world. We have a worldwide network of interactions. One absolutely key place is Cambridge University, it's on the map there, but also Tsinghua University in China and MIT in Cambridge, Massachusetts, the other Cambridge. Those are really important to us to establish a global vision of technology development. It's pretty easy to become really parochial if you just stay in one place and talk to one set of people. But by interacting with these places and places like the EPTIC Research Centre, the Etisalat BT Research Centre in Abu Dhabi, and obviously we have people in Silicon Valley scouting the companies there, scouting the startups and understanding what's happening in the valley. That's how we avoid ending up as just falling into groupthink and focusing on what we know best. We're constantly disrupted by technology evolving and emerging around the world. Okay, so these inputs actually bring us to making insights about what's going on that perhaps are different from the common wheel. So in this case, what we're looking at is how data can be used by companies and society in general. And we see quite significant problems. And recently you'll have seen that the data science community has really failed to use data correctly in predicting the outcome of various major events in elections. So obviously Donald Trump's been elected in the US, and the pollsters in the US were very clear that it was very probable that Hillary Clinton was going to get elected. Now this is a complete misuse of data, in my opinion, because it's a binary event, and assigning a probability to a one-off binary event seems to me to be a pretty bizarre thing to do. And of course, the pollsters will tell you that although they said it was 90% probable that Hillary Clinton was going to win on the morning of the election, they were allowing a possibility that Trump would win. And I've heard a pollster, a guy who ran a prediction market actually, tell me that that means that out of 10 possible elections, Donald Trump would win 1 and Hillary Clinton would win 9. And it was just the fact that it was the 10th election on the day. But of course, in the real world, that doesn't matter. We will never, ever have a Trump versus Clinton election ever again. Presenting data in this way is fundamentally misleading. Instead of using statistics in this inappropriate way, my view is that we should be using the practices of science, the true practices of science. In science, what we do is we make predictions from theories and then we test them. So science is about creating testable theories. Clearly that is a disjunct in the way that data scientists are currently behaving, or challenge the way that data scientists are currently behaving. Now, I have to emphasize that preparing this lecture, I've spent a lot of time investigating different people's views of what's happening in the world of data science, and it is a bit of a hall of mirrors, and I feel pretty tattered and torn, like Bruce Lee in a hall of mirrors here, going through this. So I don't claim that these are definitive answers, and this is just a set of perspectives on what data science is right now. So I ask the audience when I give this lecture, can anybody tell me what a data scientist does? And in general, you'll get a fairly confused response if you ask that. It's a new profession. It's something that there's a number of different practices. There isn't a settled, established professional practice around data science at the minute. And so there's a whole load of different perspectives. And if you go on the internet, you can find blogs where people produce visualizations about the practice of data science and definition of a data scientist. People do this because it's seen as a very glamorous job. It's seen as a very highly rewarded job. Data scientists are able sometimes to make very significant business impacts. And so there's a lot of discussion about what does it mean? How could I become a data scientist? What skills do I need? And you get Venn diagrams like this. I think this was the first attempt at a definition, if you would call it that. And it's quite alarming to see, while people are saying, okay, it requires domain knowledge and maths and statistics and computer science, they call it hacking, but computing skills, some knowledge of machine learning, some knowledge of how to do research. Actually, there's also a danger zone appearing on the diagram, and I think that gives a hint as to the depth and quality of the work here. Other people have tried to go down this path and produce refined definitions of this sort, and again, we see some variation from the danger zone here. It's called traditional software instead of danger zone, which I find quite funny. But in the middle, instead of data scientist, we've got unicorn, which is an alarming description of somebody, to say the least. Sometimes people create jokes out of these diagrams. So we have a data scientist here, and it all looks very interesting. And then when you read it, you find out that without expertise, it's a recipe for limited models, litigation, disaster, and abuse. A bit alarming, to say the least. And these are just selections of the different opinions about data science that are out there. This one's from Wikipedia. They've given up on the idea of a Venn diagram there. There are more complex Venn diagrams that are brought in with hot air and communication skills introduced. Clearly some people have completely lost the plot and are just scribbling on a page. And then this is a serious attempt at trying to form a very complex, a 7-set Venn diagram. And then because you can't write small enough to put the titles in, what they've actually done is numbered each cell and provided a legend. And I would say this indicates that the world in general has completely failed to define data science. And this is not surprising because data science is a very strange mix of the old and the new, and I think it's very interesting to talk about how it's come to emerge. So if you were to ask people about the coolest things in data science today, one of the answers that people would give would be probabilistic program induction. Basically using causality, notions of causality, composability, and learning to learn to create programs which represent data. And the very cool thing about this is because this is about structural learning of items in the world, it's able to learn things with very few examples. So the analogy that the people like Brendan Lake, who was the author of this paper, give is that they talk about constructing a character as a human being. And basically, they talk about if you're a human being, you'll draw a letter in a particular sequence, you'll use a particular sequence of strokes, you'll go in a particular direction for each of those strokes. If you're able to capture that as the machine, then when you see, if you capture the general expertise about constructing letters in that way, then when the machine sees a new letter, what it's able to do is to decompose it into the strokes and ordering and directions that a human would take to make that letter. And that recipe can then be labeled as the letter type and applied to any other examples of that letter that are then seen. And it turns out that if you do this with just one or two examples, you can generalize very strongly to all letters that are presented. And in fact, so strongly that this technique, when it was implemented and developed, it's beaten all the traditional techniques into a cocked hat. But not only that, it's beaten the modern techniques of deep learning into a cocked hat as well, because it's approaching the problem from a very human perspective. But underpinning it all is basically Bayesian statistics. So the sums, the maths that underpin this approach are Bayes theory. And the Reverend Bayes is not a new character. Bayes theory is not a new thing. It's not a particularly complex thing. It's not a complex thing at all. But this is a very traditional way of handling data and statistics, and a very successful one. So what really has changed? And what really has changed is the infrastructure of computing and the infrastructure of statistics that are available to statisticians and other practitioners. Back in the 1950s, industry got the opportunity to store data on a large scale. This is extremely useful to industry, very useful to commerce. It's enabled huge amounts of our economic growth, although economists can't actually manage to measure it. But I would argue it's fundamental to the success and wealth we see around us today. IBM, when they built the first commercially available hard drives, wouldn't actually sell them to you. They were too valuable to sell. They would lease them to you. They were enormous. And they stored what we would think of as trivial amounts of data nowadays. And you know, to illustrate that, on the one hand, we can talk about how much it would have cost and how much space you would have needed to have the same storage as an original iPhone. And the answer is, when you do the sums, about $100 million a year and 10,000 square feet. So it's an enormous blow to realize you'd have had to do that. And also, you know, you can look at various measures of how much of the world you'd have to cover in order to store the equivalent amounts of data that you find on modern Hadoop clusters. And we can look at our cluster in BT, and we can say that to use old-fashioned storage, we'd have either had to use an entire country, like the Principality of Liechtenstein, or we could have built a road round Australia out of our IBM hard drives, and that would have given us an equivalent size storage capability to the one that we have in a small shed at Adastral Park right now. The other way that things have changed is that things have got a lot faster and a lot more accessible and a lot cheaper. So this is a picture of Jim Gray. Jim Gray was largely responsible for inventing relational databases, which are the standard way of storing and querying data that's used in the commercial world today, at least in 2017 and 2016. And I looked up some notes that Jim Gray had left. Jim Gray unfortunately died a few years ago. He disappeared on his yacht. But he left a whole litany of information and notes behind. And I was looking through some of these on the internet, and I discovered that he was in a talk where he was being talked to about this new Infomix machine, and it was in 1993, and the people were using about 9 nodes. It was a distributed database. It could process about 23 megabytes per second when it was scanning its tables, and it cost about $100,000 to buy this machine. Now, probably the smallest unit of similar type computing that it's possible to buy on Amazon Web Services, you can get an Impala instance for about $10 to just rent it, set one up, and it goes about 1,000 times faster. And of course, it's about 10,000 times cheaper. There's an astonishing change in a very few years. So looking at going faster, the other thing that goes a lot faster is the capability of people. So measuring software productivity is extremely difficult, and it's very hard to find reliable data, or any data, in fact, on how software productivity is improved. The data I can find, or have been able to find, fairly dodgy estimates from a consultancy online. But the indications are that there has been a radical improvement in software productivity, and I think this is widely agreed in the world, that in recent years in particular, we've got a lot better at writing software more quickly. And from my perspective as a professional, through my career in the last 20 years, I've certainly seen a complete step change in my ability to produce software at speed, and especially software around data analytics. So when I was finishing my PhD, I used to use tool chains around Unix tools to format and move data around on a Unix system. I used to use C++ to create algorithms, and then I would analyze the results with a whole tool chain of other Unix tools and plotting tools. Now I use a tool called R. It's all in one graphical environment. I can do things that would have taken me hours without taking into account the processing time, but just in terms of setting up and asking it to do the tasks. It would have taken me hours. I can do those in seconds now, and I can do jobs that would have taken me weeks and weeks of work to do back 20 years ago in an afternoon. And so this is a huge change for the better in terms of what a data scientist can actually achieve and do. So to sum that up, what I would say is what's changed, what's caused the emergence of what we call data science is the fact that we have more data. There's tons more data. We can store it practically and cheaply. We can process it much more quickly. Moore's law has helped us enormously. We've got the opportunity to churn through vast data sets at speed. And as individuals, and especially as teams of individuals, especially as teams, we can deliver code much more quickly than we did in the past. And I'd like to just talk about the teams thing. Again, 20 years ago, we didn't really have an infrastructure for working together in software development or in analytics projects. And now there's a whole range of tools which mean that you can build and orchestrate and manage a team much more effectively than just a few years ago. And also, software professionals have got much more open and much more enthusiastic about using these tools as well. It's something that we see a lot of pull, especially from younger recruits, to do. They want to be part of a team that's run in this way, and it makes a huge difference. So what does this all mean? Well, I don't have a glib, clear answer. I would say that what it means is that data science is a running proposition in the world. It looks different from how it did 20 years ago. You know, things have changed. There is a change in the world. And it's enabled projects of this sort. So I think it's illustrative. Rather than saying, I've got a magical definition, I can say, you know, the world now allows us, these changes in the world allows us to implement projects which are quite different from the kinds of projects that we used to do. So here's an example of a project that we've done at BT, and this is about managing the telemetry off the access network. So this is very different in terms of scale and challenge from a data science project 20 years ago. In that we're bringing together the data off many, many systems that contain data from different domains. And each system was developed to satisfy a particular use case. So the data asset is there to satisfy a use case like running a maintenance schedule or working out the age of the equipment, or managing the way that the line is provisioned with data from the internet. In order to set up a connection, you have to know how fast a line would go. The line telemetry can tell you that, and there are systems that use that telemetry to manage the connection speed. And what we're able to do is bring together all those bits of data and put them in a massive data store, supplement them with real-time telemetry out of the network, which is a very large-scale telemetry feed. And then we use this single asset to then hydrate all sorts of applications which were completely unforeseen when the original systems were built. And that's a massive change. First of all, 20 years ago, we wouldn't have had this plethora of pre-existing systems. They just didn't happen. The world wasn't digitized. And now we've got all these subsystems which we can draw data out of. We wouldn't have been able to store this vast amount of data. It just wasn't possible. And we wouldn't have dreamt, we wouldn't have had the capability to build a data asset and then exploit it, to mine it for the data, to build off applications from it. And this has led to some specific changes and differences, specific challenges around systems like this. And this is sort of to try and summarize the common pattern that I see. What we see is two new kind of requirements. One is the requirement to do what we would call pipeline engineering. So we have to build and manage data pipelines into our systems. And this is an engineering challenge. And to meet it, we have to mediate a whole set of different systems. We have to manage the flow of data down them. And then get the data into a system where it is useful, which is the big data system at the end of the tool chain. The other challenge is to manage the models which are generated and the information which is generated out of the big data system. So there's a whole range of different users, different consumers that sit on the other side of the big data system. Some of them are other programs, so some of them are other systems, and some of them are people using spreadsheets. Some of them are people using novel data analysis tools. But what we have to be able to do is to manage all the models that are generated out of that in order to understand the differences between them, to understand why they're saying different things or what the differences are. Now, why is the pipeline engineering important? The pipeline engineering is important in this situation because things go wrong. Because what happens is that if you don't do the pipeline engineering, if you don't look at the evolution of the data coming out of the systems, if you don't manage that, then you discover that in your data you've got junk. You've got wrong readings, you've got miscalibrated readings, and you've got missing readings. And this basically renders parts of your data set wrong and irrelevant. And this can destroy the utility of all the analysis you do. Now, this is something that's absolutely standard and familiar to any scientist, okay? So physicists, biologists, chemists, anybody doing proper science will know that uncalibrated instruments, unmanaged instruments are useless, right? Your data is unreliable. Nobody will believe you. Your PhD examiner will simply close the book and say, I can't do this anymore. It's all got to stop. You won't get your papers published. It's nonsense. It's just bin it, right? The calibration, the proper use of the tools is absolutely fundamental to doing proper science. But in business, This is widely tolerated. This is not known, not understood, not managed. And it's quite common for people to use found data, to use data with holes in it, because it's the best thing that they've got. It's the only thing that they've got to give them clues, to give them some sort of non-gut feel approach to the problems that they face. But, you know, it still absolutely renders it faulty. And what we need to do is to be able to detect that's going on and to manage the quality of the data into the data stores. Model management's really important because every time that you take a model from data, every time you simplify something or reprocess it, you're making a whole load of choices. And these choices need to be recorded and tracked because they explain the differences between the different models that are being evolved and used. And that's really important because in some contexts, a model that's created in a particular way with particular assumptions is perfectly fine. Okay, so for operational use, to change the controls on a particular piece of equipment that's not life-threatening, but you want it to perform just as well as you can get it to perform, perhaps you can just make the assumption that missing data doesn't matter, okay? Because by making that assumption, there's a whole load of utility that you're going to get a much better performance out of the equipment than you otherwise would. When you're going back and making, for instance, a procurement decision about the different performances of bits of equipment, if you've made that assumption, you're completely at sea. And knowing, therefore, that the assumption has been made, knowing that there is a different model with a different set of assumptions where there's been a different treatment, maybe it takes longer to treat the data that way, maybe it's more expensive, or maybe that hasn't been done and you need to get it done is absolutely fundamental. And this is actually a screenshot from a project that collaborators at MIT have been working on recently that attempts to tackle this issue. And this is the Model DB project. And what they're doing here is, as I say, annotating data models and then trying to record them very much in the same way that people record snapshots of their programs in version control systems, and they're trying to apply version control to model management. Of course, these considerations, the pipeline, the model management considerations and the pipeline considerations that I've mentioned, there are other forces that are out there as well that impact them. On them. One thing around model management is the kind of considerations about privacy and ethics, about access, so authentication, about knowing that people have accessed your models, that the models haven't leaked, that somebody isn't using the model to infer what's going on in the data on the other side of an API. Those are fundamental things that you need to apply when you're talking about personal data. And data ethics really impact across the whole data science spectrum. But I think especially when it comes to model management, you know, the personal data makes it very different, and you have to move beyond the mechanical, these are the assumptions we've made, these are the problems with this model, to also, and this model is private, this model shouldn't be used for these purposes, this model shouldn't be available to these people. The other thing is when you're talking about deriving models and data pipelines, when you're working with commercial relationships, you absolutely have to know that your data is partitioned away from between different customers, between different use cases. So, you know, for instance, if financial companies were sharing an infrastructure and they discovered that their data was being shared or intermingled or used for different purposes, immediately they would withdraw from that infrastructure because their data is their competitive advantage. So we absolutely have to have strong control and management of the data pipeline from that point of view as well. Okay, so these are the challenges that come out of doing a modern data science project. Okay, so you know, this is one project, the Access the Access Network Telemetry project. It's using all the modern forces of data. We're doing data science. We identify some clear differentiating challenges that come out of that. And basically what we're saying is we need to understand what's going to happen to the data, how it's going to happen, where it's going to happen, and when it's going to happen, and we need to understand the same things about the models. And the issue is, though, that data scientists and data science, the kind of activities that data scientists do in the literature, don't address these issues, okay? Data scientists are concerned with the end product, with getting the value out of the data. They're building a system to just extract that data. Understanding the behavior of the data, which is the key problem, requires another perspective. And again, I think the perspective that's required is to move beyond data science and move towards a science of data. So the question is, what is a science of data? What am I talking about when I talk about a science of data? Well, one way to understand this is to understand the kind of artifacts that a scientist of data would be trying to observe. What is it that we're doing in science? What we're doing in science when we do a biology project or a chemistry project or a physics project is that we're trying to characterize nature. We're trying to delineate the features of things in order to build a better understanding from which we will create theories which will have predictive power, okay? And that's how we test the theories, because they've got predictive power, and then we're able to say that validates the theory. That's the principle of science. So what are the artifacts? What are the things that we would try to characterize a piece of data by? How can we observe data? So first of all, can we value data? Well, that's an extremely difficult one. What is the value of a piece of data? Another thing there is, does the data provide insight? Is it informative? What is the significance of a piece of data? Is the data anonymized? Is that a characteristic? How long would it take for this piece of data to flow across an infrastructure, across a company? Can we observe constraints on its behavior? Can we be diagnostic and prescriptive about the data assets and about the data themselves? So fundamentally, can we say this data asset is of more use than this other data asset? Can we say that this piece of data is deficient in some way compared with another piece of data? Can we rigorously measure and determine those properties from our data assets? So at different levels, can we understand the data items themselves? Can we understand the data sets that they're within? Can we understand the overall infrastructures that contain the data sets? And can we understand the ecosystems around those data infrastructures? Can we understand how human teams interact with the data infrastructures that they're using? And these are the kind of characterizations that I think would be significant and useful to be able to make in a commercial environment. So again, trying to find out what a science of data would look like. Would it be like physics, or would it be like biology? Okay, in physics, this is the archetypal science. This is the great success of the 19th and 20th centuries. That's given us the revolutions that took us to the moon. It's predictive. It's very specific. It's about studying multiple systems, and versus biology, where you're describing things, it's general, and there's only one system. I think I've given myself away. I think that the best idea we've got really with data science the science of data is to try to describe things. I think that the more important thing is that in biology, huge numbers of teams can do the same experiment and can gather the same results. So there are millions of Petri dishes across Cambridge, across the world. All sorts of things are going on inside those Petri dishes. And different people can measure it in different ways. There's a vast variety of possible experiments that people might conduct. Whereas in physics, what we're now seeing is a centralization of the experiments. We're seeing individual massive instruments being used to generate vast data sets, which are then taken away by individuals to look at, and a much more centralized and organized community. And I think that whether a science of data is going to look like biology or physics is going to be a great deal to do with the way that it's organized, and whether it's going to be to do with whether it's centralized or whether it's distributed across the world. Will it be the case that different labs, different organizations will be able to evolve their own ideas, evolve their own practices rigorously over the data assets that they own, or will there be very large central data assets that will be studied by specific teams, and institutions? And I think this is very much in the mix at the minute, because I think that we're seeing a balance between cloud technology and communication technology. The big cloud vendors a few years ago, it really looked like the big cloud vendors like Google and Amazon were going to just dominate the data world, that there was going to be a phenomenon of data gravity, which was just going to bring all the data sets of the world into a very few places. Subsequently, we've seen a slowdown in the economics of data storage, and we've seen a continued acceleration in the economics of data communication. And the interesting thing there is that if that continues, maybe it will be the case that the effects of data gravity will not be as strong as they were in the past. And if that is the case, then we will see many companies, many individuals being able to own their data assets, localize their data assets, and effectively process them themselves and evolve these ideas about a science of data. Okay, so that's the economic argument there. So those are different perspectives, theoretical perspectives or opinion perspectives on what a science of data would look like. That all counts for nothing. The question is there any work on this? And this is the work that's going on in Rob Claxton's group. I talked about Rob at the beginning of the talk. And this is a paper we published this summer. This is just one of the figures from it. And what we're doing here is that we're using graph analytics to examine the contents of a data store. And what we're looking to do is to say, can we characterize the data tables in our data store and use that characterization to group them together and to understand the interactions between them? And the purpose of these groupings and these understandings is twofold. One is the act of data discovery, to be able to say what links are there between the different data assets used by different groups of people that could be informative and instructive to them in their analyses, right? So if you've got Group A using a data asset and Group B using a data asset, and it turns out that Group A and Group B have social interactions, they have organizational interactions, it might well be that the connections between the data resources that those two groups are using allow you to tell one group or the other, hey, actually, Group A hold data which is really useful to you in Group B. And this sounds really trivial, but actually it's the case that when you're confronted with a massive data asset, it's really hard to determine what will be of use to you and what would help you solve the issues that you've got in front of you. And we see this, we have evidence for this, because we see repeated replication of data items in data stores by different groups and different analysts. So clearly, they need the thing. They go out and get it. They manage it. They don't know it's available elsewhere, because otherwise, why wouldn't they just use it? So this is a way of helping detect that situation and preempt it. The other thing that we were very interested in is, were we able to see hidden routes through the data infrastructure that would allow people to effectively backdoor knowledge and information that they shouldn't be able to by making inferences across the data tables. So doing this many-step linkage analysis allowed us to see where complex queries, which were not imaginable to the users of the data store, were possible, that would allow tables to be linked together, which then allowed inferences that were partitioned away by security from the users of the data store. So we were able to then detect routes of inference that were previously unknown in the data store. To give you an idea of the scale of the graph here, this is more than 3,000 tables in a Hadoop cluster. And to give you an idea of the scale of the challenge, this was our old research Hadoop cluster that we had closed. And before we closed it, we took a snapshot of the data out of it so that we would be able to use it for investigatory purposes like this. So we knew that this was a dead data asset and that there was no data of any, there was no personal data, nothing in it at all when we did this work. So we knew ethically it was fine for us to do it. But the point here is, this was 3,000 tables in that research cluster, and this is a very small machine compared with the assets that are out in the wild. And at BT, we've got several databases which have got more than 20,000 tables in them, and that gives you an idea of the scale of the challenge of management and understanding for those assets. Okay. So these are the kind of, so I've talked about the kind of applications, the inference across the data tables that can be made. The other thing that we can do is we can characterize the data graph in terms of numbers. So we can characterize it in terms of its shape, and we can evolve some description of the data asset in abstract terms. So beyond drawing a pretty picture and seeing patterns, we can actually describe quantitatively what the characteristics of the data asset are. And this is useful and potentially important, because this is the kind of thing that then can be used to be diagnostic about the data asset. So we can actually look at the data asset and we can measure it in these ways. And we can say, look, this is unlike other data assets we've seen. Okay? We're not at the level of being able to say, and here is the prescription that you need to follow, because the science has not evolved to that level. But that's what we want to do, because the suspicion is that different databases suffer from different pathologies of use and different inefficiencies, driven by different organizational forces, driven by their history, driven by user behaviors. But if you're able to measure and characterize those, then the hope is that you'll be able to detect that, determine that there's more efficient or better ways of working, and prescribe changes that over time will reduce the issues that you're seeing. And again, there was a live example, a very old example, one of the original data warehousing systems that we implemented at BT. When it was initially implemented, the art of data warehousing was very weak, as a decade ago or more. And rapidly, the data asset blossomed into over 90,000 data tables. So this is a very widely used system, and it ended up with 90,000 tables on it. And it was almost impossible to know what the use of any of those tables was, where the data about different aspects of the business process actually had gone to in that infrastructure. And what we had to do was to invest a significant amount of money and a huge amount of time in actually correcting that by hand, going into it and working through all those problems and producing a homebrew prescription for sorting it out and reducing it back down to about 25,000 tables. Now, so that shows, you know, that there are these problems, these things can go wrong, and are going to need fixing. Here's a translation of that information, the graph data, from numbers into a tool, and again, this gives some insight into the kind of things that we think a science of data might be able to yield. And this is a tool that is a dashboard about a data asset. It doesn't talk about what the data in the asset does, but it talks about what the asset looks like, and it allows you to press buttons and inspect the asset from a top level and make interventions in it. And the specific interventions here are these detection of inference chains in the database, and then the application of security controls to preempt those. The end game for the work at BT is to move towards what we would call an observatory-based approach to data science and science of data. We believe that a science of data is about individuals being able to measure and characterize data items, make prescriptions, make diagnoses about data and databases, and therefore produce high quality testable predictions out of those assets. But we also believe that something that is often neglected in a discussion of science is the social aspect. And for me, a fundamental thing about scientists is that they work together in communities. They work together in communities to establish norms of behavior and to establish practices which allow a more effective and more productive furthering of the state of the art in their particular practice. And this is something which is notably absent from data science at the moment. Instead of that, what we're seeing in data science is a market-driven validation of individuals. What we see, both in business and in the media, is the winner with the best visualization, the winner with the best self-publicity. It's very, very hard to win a business argument against somebody that has apparently clear data, beautifully presented. People talk about data storytelling, they talk about establishing a narrative. The thing is that stories are often just that. They're just stories. And if you've made a major decision on the basis of a story, it's extremely unfortunate. And a lot of people will have bet money based on predictions of election results. A lot of bookmakers will have paid out money on the basis of odds that were established as the basis of data science insights. For instance, a major bookmaker paid out on a Clinton win a week in advance of the election. So 1 week before the election, one of the major bookmakers actually paid out on Clinton bets. That's an incredible mistake. They did it because they were sure she was going to win. They did it because it was a great publicity stunt for them. They lost a lot of money because somebody told them a story. And that can happen in science. Science isn't a perfect institution. People do come up with stories that subsequently prove to be wrong, but it's rare. And these stories are well known because of their rarity. And instead of that, a much more common story in science is that somebody comes up with a narrative that's a bit funny, a bit suspect, and that person's peers instruct them and inform them that that's the case, and they go back and think again, and they do something else. And eventually, if they're right, they come up with an unimpeachable, solid, validated piece of research which is then believed. And if they're wrong, we just all forget about it. But that is the institution at work. Okay. So that's all I really have to say about the topic. I hope the lecture was useful. Just to reiterate, what we're after is a way to generate theories with a track record of making testable predictions, the practice of science with data. In order to do that, I think that what we've got to do is evolve a whole set of scientific approaches to the discipline of data science, a science of data. We've got to establish a much stronger understanding of data itself, of the behaviors of data, of the evolution of data, and in the future, although we haven't done much work on this yet, I believe there's an equal amount of understanding of models and predictions that are required as well. I think I should leave it there. Thank you very much for your attention.